Okay, so looking at this first one, I don't think anybody got it all completely correct, so it's worth certainly talking about this. Again, the symbols, the N is natural numbers, the Z is integers, the Q is rationals. Irrational, it says, and the R is reals. So right away, anything that can be written as a decimal is a real number. So all four of these numbers should have been checked for reals, right? Irrational means that you can't represent it as a fraction. So the decimal would be non-repeating, non-terminating. So certainly pi, anything with a pi in it is going to be irrational. And if you have the square root that can't be simplified anymore, like the square root of 5, that would be irrational. And you can't, if you're irrational, you can't be any of these other higher levels. You can't be rational, you can't be integer. Luke, I got one for you. And you can't be a natural number. So these first two should have just been irrational and reals. Now, 8.4 repeating, there the repeating decimal tells you that this is rational. If it's a repeating or terminating decimal, it's going to be rational because you can be able to write it as a fraction. So we have real and rational here. 6 is rational, right? You can just write it as 6 over 1. If you're a decimal, though, you can't be an integer or a natural number. So 8.4 repeating is gone now, so it's just Q and R. And then 6, well, that's an integer, and it's a natural number. Natural numbers are just the positive integers. So 6 should have been everything except for the irrational. For the percent error calculations, it seemed like most people had it written down in their paper correctly, but maybe we somehow struggled to get it through the calculator. So the way I would do this all in one line on my calculator. So I'm going to do number to get the absolute value symbol, and then alpha y equals, and use that horizontal bar. So A is the approximation and E is the exact. So 440 is my approximation. Tells you they are exactly 486. So I would type it in this way. I think even saw a couple of people like write this down correctly and then somehow not get the proper answer to come out of here. Now this gave me a fraction. Oh no, what do I do? So you could just retype the fraction as a division problem, and that'll give you the decimal. Oh my goodness, what did I do, Mr. Kulik? Dumb. Look what I did. 486 was the exact. I put 440 on the bottom though. So there's that. Again, you could just retype the fraction as a division problem. Thanks, dude. Luke, for you. So there's your percent error. Alternatively, if you have something like this, you can always just do math, and then if you choose the decimal command, it just convert the fraction to a decimal. So you can do it that way also. So 947 should be the correct answer. If you didn't round this correctly, I marked down because it says rounded to 3 sig figs. So if you said 346, I marked off because you should have rounded that up to 347 or 947. If you wrote it as 9.5, I marked down because you have not enough sig figs, right? So just be careful on the directions. Here we said Victoria approximates the area of a circle with radius 6.5 is 110 centimeters squared. The formula for area is this. What is the percent error to the actual area? So again, I'm going to type in my percent error. I'm going to just steal this and edit it. So my approximation is the 110. The exact is going to be pi r squared pi r squared, since it's a circle. So this should have been 17.1%. Again, 3 sig figs there. Notice that I didn't get a fraction come out of this when I did it. Why didn't I get a fraction this time? Right, when I did that before and I typed it into my calculator this way, they gave me a fraction, right? But I did it this way, and I didn't do anything different, but I didn't get a fraction. Yeah, because of the pi. What kind of number is this? It's an irrational number. It cannot be represented as a fraction, even though I use the fraction mode. It's like, nope, can't do that. You're getting a decimal. Everybody's okay? That's a good question there. So here we're asking you to just do some operations in scientific notation. What's going to be the easiest way to do this? I'll tell you what I would have done is I would have just typed this into my calculator. So you could have reported this as, you could have, again, we want scientific notation in our answer, but you could have reported this as 4.91266 times 10 to the second and given me all the decimal places. Why would that be okay? It's an exact answer. That's a terminating decimal. So you could give me all the decimals there and it's fine, because it's exact. Or you could have rounded it to 3 sig figs and just called it 4.91 times 10 to the second. And I think if you put your calculator in scientific mode, it'll give you your answer as a scientific notation for you already, so you don't even have to move any decimals. What? So if we do the same thing, if I do this divided by this, and I'm still in scientific mode, look at that. Just gave me the answer in scientific notation format. I don't even really have to do much. I just have to round it appropriately. Could I give you all the decimal? Could I give all the decimals this time and have it be correct? Sure looks like there's probably some more decimals than this because it's a division problem rather than a subtraction problem. So there's probably a kooky, crazy decimal there. I would round this to 3 sig figs rather than listing all the decimals because I don't think that's going to be the exact answer. Is this okay? For this one, I think most of us did fine here. All you really had to do was plug 108 into the TF in the formula. Now, before I press enter, what am I going to remember to do here? Change my mode back to normal so I don't get a scientific notation answer. Unless I wanted a scientific notation answer, in which case that would be fine to have left it there. So there's the decimal. Again, rounded to 3 sig figs, I'd call that 315 Kelvin. I think everybody got this answer right, but a lot of us messed this piece up because you did 4 yards is 3 feet and then 12 inches. So I have 144 inches. I divide that by 7, and I have 20 pieces of rope, and 0.57 piece of rope, though, not inches. A lot of us put 0.57 inches here. The way you could do that is you can strip off the ones place, and then if I multiply this by 7, that's the leftovers. So it'd been like 4 inches of leftover. And then here, I don't think anybody got the correct unit. So 5.3 times 4.8 times 6.7, right? So there's the number of cubic meters. What do I have to multiply this by to convert it into cubic centimeters now? How many cubic centimeters are in 1 cubic meter? Nope. How many centimeters are in 1 meter? 100. But it's cubic, right? So it's 100 to the third is your conversion factor. So that's the number of cubic centimeters there. You could list that exactly, or you could have rounded it to 3 sig figs or written in scientific notation, or any of those above would have been okay. Right? Because ideally, you could have converted each one of these to centimeters separately, right? So each one of these would have gotten multiplied by 100. So you need to multiply by 100 3 times, 1 for each dimension. I know. So this one went pretty okay. When you have an exponent of an exponent, the exponents multiply. So this one becomes a to the negative 2. And then when you have exponent times an exponent, you add them together. So 3 plus 7 plus negative 2 is a to the 5th. Here, when we have an exponent of a product, the exponent applies to each factor of the product. So you should have 2 to the 3rd, x to the 15th, 3 to the 3rd, y to the negative 6th. And then you'd move, because we want positive exponents, that y to the negative 6th would become a y to the positive 6th in the numerator. But the 2 or the 3 to the 3rd should stay down there. I don't think anybody had a problem with that. If we round to the 100, you should have gotten 350, 500, and that's fine. Since it asks you to round to the 100, they tell you the amount of rounding, so the sig figs wouldn't matter in that case. We want then you to re-round or round this number to 3 sig figs. So the only way to do that is to use scientific notation, right? Because this would round to 350,000. But 350,000 only has 2 sig figs. You'd have to write as 3.50 times 10 to the 5th, right? Because if you have a trailing 0 after a decimal, that's significant, as opposed to a trailing 0 before a decimal, or with no decimal, which is not significant. Rewrite the number in standard form, rounded to 5 sig figs. So 5 sig figs would be rounding right here at the 7. So I'd call that 3.5048 times 10 to the 5th. And then this last one, I think everybody did correctly, so we don't probably need to talk about that. We did a bunch of those in the homework before the quiz, so I think that's why everyone was like, yeah, I know what to do with this, buddy. Okay, let's get rid of that. And I think we're ready to start here, section 4. This is the last section in chapter 1. What's that mean for next week? Chapter 1 test. I know, they're all just coming fast and furious here. Here's the good news, though. Is the Chapter 1 test going to be much different than the quiz? No, man. It's going to be almost the same thing. So, we just went through the quiz. Should have a good idea of like the stuff you need to clean up, right? Okay, so we did the 1-3 stuff. In 1-4, we're going to be talking about exponents and logarithms. So I want to just start with some basic properties for exponents. So these guys are things we should remember from our Algebra 2 class, or even I think we redo these in pre-calculus even. So if you have two numbers with the same base and different exponents, and you multiply them together, we simplify by keeping the base the same and adding the exponents. If you have two numbers with the same base but different exponents and you're dividing them, we can simplify by keeping the base the same and subtracting the exponents. If I have an exponent of a product, that exponent should apply to all the factors of the product. Or you can think about it the reverse direction. If you have multiplied two things with different bases, but the exponent is the same, you can keep the exponent and multiply the bases. Similarly, the exponent of a division problem applies to both the numerator and denominator of that division problem. Or if you're taking two numbers with different bases but the same exponent and you divide them, you can keep the exponent the same and just divide the two bases. A negative exponent makes a reciprocal. And if that negative exponent is in the denominator, it would just move it to the numerator. Again, we're just making a reciprocal. If I have an exponent of an exponent, we multiply the exponents. Fractional exponents are equivalent to radicals, so a to the 1 over n is just the nth root of a. So like the square root of a is the same as a to the 1/2. If I have a numerator and a denominator in my fractional exponent, the numerator is the exponent and the denominator is the index for our radical. And then anything other than 0 to the 0 power is 1. And anything to the first power is still itself. We should have probably had an extra couple of criteria around here where a can't be 0 here or here, and b can't be 0 here, a couldn't be 0 here, and a can't be 0 here, just to clean up the undefined possibilities, right? Like we can't have a 0 denominator. 0 to the 0 is actually, what's 0 to the 0 equal to? Not 1. Undefined, yeah, not 0. It's actually different than undefined, though, even. It's called indeterminate, which means that, like, I can set up two different problems that are, like, 0 to the 0 and simplify them down to different things, which is weird. If you're interested more in that idea, you should take calculus, because you'll talk about indeterminate forms in that class. Megan, you missed out. But these should all look familiar, right? These are all things we've seen probably a couple of times at this point. So let's talk about logarithms here. We're going to start with the definition of a logarithm. The definition says that the exponential equation, b to the y is equal to x, is equivalent to the logarithm or logarithmic equation, log base b of x is equal to y. So notice that I've drawn some arrows showing you kind of how the numbers in the two equations switch around to create an equivalent equation. But the takeaway is that the base of the exponent has to be the same as the base of the logarithm. The output of the exponential is the input for the logarithm. The input for the exponential would be the output for the logarithm. So some basic properties of logarithms and then their exponential equivalent. So if I take any log of 1, that's equal to 0, Because if I rearrange this, it would just say b to the 0 is equal to 1. Well, that's an exponential property, right? We know that. If I take log base b of b, that's always going to equal 1. Because again, if I rearrange this using my property logarithms, I'd have b to the first is equal to b. If I take log base b of b to the y, the log base b and exponent base b cancel, leaving us with just y. Because again, if I rearrange this using my definition, I'd have b to the y equals b to the y. Oh, that's always true. And if I had b to the log base b of x, that should simplify just down to x. Again, exponent base b is going to cancel logarithm base b. Or if I try to rewrite this using my definition, I would say log base b of x is equal to log base b of x, which, okay, of course, that's vacuously true. Is everybody okay with these basic properties of logarithms? There's two logarithms that are special that we give special names and get abbreviations for. The first one's called the common logarithm. Anybody remember what that looks like? So it's log base 10, but we don't ever write the 10, right? We just write log. But you got it. So anytime you see log with no subscript, that just means base 10. Hopefully you remember that from previous Algebra 2 and pre-calculus courses. We talk about it in both of them. The other is the natural logarithm. What's the natural logarithm? Log base, Megan? E, good. And how do we abbreviate the natural logarithm? ln. Yep. So if you see ln, that's not one n, that's the letter L. And again, that means log base e. E being that irrational number like 2.7, yada, 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 yada. I never remember all the decimals. It's not like pi where you've done 3.14 so much on your calculator before you had a good calculator that you know you remember it. E you don't see until you have a good calculator with the E already built into it, and I never remember the whole decimal. Okay. So just showing you on your calculator again, we have the log button is right here, and the natural log button is right below it. These are some great PowerPoints. All right. Let's run through a couple examples. Let's say we want to evaluate log of 100. Pretend we're going to do this without using our calculator. So the first thing I would do is I'd want to write this as a logarithmic equation. So I'm going to say log of 100 is equal to x. Everybody's okay with that? And then I'm going to remember that log is really log base 10. And now I'm going to rewrite this using an exponential equation, my definition of a logarithm. So that's going to tell me 10 to the x is equal to 100. And then, okay, well, 100, I can want to try to rewrite this 10 to the x and 100 so that they have the same exponent base. And that should be easy, right? Because 100 is just 10 squared. And now since the bases are the same, the exponents have to be equal, so x would just have to equal 2. Again, we should hopefully remember doing this last year in pre-calculus, if not the year before in Algebra 2. I understand some of us that were in the regular Algebra 2, maybe you didn't get quite that far in your Algebra 2 class, but we did it last year in pre-calculus. I made sure we got it done. So we did do this, right? With the logs, we remember? You could shake your head if you're in my Algebra 2 or trig class, pre-calc class, where we did this. right? Because you didn't do this in algebra, correct? Regular algebra 2 kids, but we did it last year, right? I tried to go slow and do a good job because I knew we didn't do it before. And it was okay, right? It was hard because it was the first time seeing it instead of the second time seeing it, but so as a result here, we can say then that log of 100 is 2, right? Should feel a little bit more familiar seeing it a second time. Should we do another? Yeah, let's do another. Let's say we want to do log of the 5th root of 10. Again, we're going to do this without a calculator, just for practices. I acknowledge fully that you could just type this into your calculator and press enter and it would give you the number. I understand. That's not the point of this exercise. It's to like get used to manipulating the logarithm so we understand what these things are really doing. So just like the previous problem, I'm going to start by rewriting this as a logarithmic equation. So I'm going to say log of the 5th root of 10 is equal to x. I'm going to remember that log is really log base 10. And then I'm going to rearrange this so that it's an exponential equation. So I'm going to have 10 to the x is equal to the 5th root of 10. You like that with the arrows? It's so fancy. Okay. So now that I'm here, I want to rewrite this so that I have the same base, and these are both exponential. So this one I don't have to do anything to, but the 5th root of 10 I need to write as 10 to some power. What power of 10 is the 5th root of 10?
1/5.
10 to the 1/5, right? Remember that the index of a radical, if we have a radical around a number, we can make a fractional exponent where the index is the denominator. Now that we have the same base for our exponential, the exponents we can just set equal to each other. So x is 1/5, and in the end we can say then the log of the 5th root of 10 is just 1/5. And we'd see that if we type this into our calculator, that's exactly what we'd get if we typed it into our calculator, right? Here. You remember how to do that on your calculator? So do log, and then how do you get a 5th root? And press math and choose option 5 there. And that'll allow me to type any index in that I want. And there's 0.2, where it's like, hey, Mr. Kulik, you said it was 1/5. Well, if I do fraction and convert that to a fraction, it is 1/5. Some of us probably recognize 0.2 as the same thing as 1/5, which was great. Okay. Next up, oops. Where do I want to be here? This, oh, boogers. I don't do very many PowerPoints, so I never remember what button I have to press to pick up where I left off. All right, one more, I think. What if I wanted to do log of 1/1000? How do we start?
Equal to x.
Yeah, we write it as a logarithmic equation. Good, then what?
Put the base 10.
Yeah, we remember it's base 10. Excellent. And now we can
Do the arrows.
do the arrow stuff. So use the definition of a logarithm to rewrite this as an exponential equation. So the exponential equation would be 10 to the x equals 1/1000. There's the arrows. That's so pretty. And from here, what do we need to do next? Try to rewrite these two numbers so that they have the same exponent base. So 1 over 1,000 I want to rewrite as 10 to some power. -3 would be the power. Excellent, Megan. So hopefully you can see that it has to have a negative in the exponent because I have a 1 over, right? And then ideally you'd recognize that 1,000 is 10 to the third, right? So 1 over 10 to the third is 10 to the -3. And since now the exponent bases are the same, what can I say about their exponents? They're also equal. So we can say then log of 1 over 1,000 is just -3. Again, you get the exact same value typing this into your calculator. That's not the point of this. The point is to practice using the definition of logarithms and some of these exponent properties just to get reacquainted with this stuff. Because it's been an entire summer and all that math kind of drifts out while you've been, like laying on the beach all summer or something. Christian's like, that's what my summer was. Beaches and forgetting math. I'm just joking. You probably remember your math. Could be a lot of beaches, though. All right. Let's look at a slightly different version here. Here we have 10 to the log of 6. So this one's going to be a little bit different because we're going to start with an exponential equation, right? So that's what I'm going to start by doing. But just like we did before, I'm going to remember that log of 6 is really log base 10. Oh, okay. No, I'm not. I'm going to do this first. All right, that's fine. I'm going to rearrange it into a logarithmic equation. So this just has log base 10 of x is equal to log of 6. So log base 10 of x is equal to log of 6. Now we'll remember that log is just log base 10. And now since the logarithms are the same, what can I say about the inside? They have to be equal. Or just that 10 to the log of 6 is 6.
So we're going to say that since we know log is 10, that 10 times.
Well, it's 10 to the,
10 to, yeah.
right? Not times, it's an exponent. But yes, it's just 6. Yeah, they just cancel out, right? That's what you're saying? Yeah. That's the way I look at it. It's just I just cross them out and say it's equal to 6. But this is just practicing using the definition and the properties is the point of what we're doing. Not so much like, can we just simplify this quickly? If I did, it would just worry about using our calculator. The point of this is to practice the properties. All right, I think I got another example here. Yep. So here we're going to be solving a logarithmic equation. So here we have log of x is equal to 4. So again, I'm going to start by remembering that log is what base? Base 10. And now I'm going to use my definition of a logarithm. So this would say 10 to the 4th is equal to x. Or you could think about doing exponent base 10 to both sides and canceling the logarithms. It's equivalent. Look at the arrows, guys. These PowerPoints are a thing of beauty. I'm not going to take credit for doing this. Mr. Chun left these for us. I know. He did such a nice job. And then obviously 10 to the 4th is just 10,000. So that's our answer for x. What do you think? Should we do another? Yeah, let's do some more. How about if we have log base 2 of x is equal to 5? So again, we'll start the same way by trying to rewrite this as a exponential equation. So I'm going to have 2 to the 5th is equal to x. Well, that's just 32. Oops. And we're done. Yay! Or you could think about doing exponent base 2 to both sides. Same process. Let's talk about a couple of properties of logarithms. So another property of logarithms is called this change of base formula. So what it does is it allows us to take log of base b and rewrite it as the log of any base. So if I take log base b of r, I can rewrite that log of a, or log base a of r divided by log base a of b, where log base a, I get to pick what a is. What would be the most common choices for a? 10 or
Natural.
e to make it the common log or the natural log. Why? Because those are often built-in functions to your calculator, right? Back in Mr. Kulik's day, we didn't even have a log button on our calculator. We had to look all these things up from tables. It was lots of fun. When we got the scientific calculator, had log and natural log built into it, it was really exciting. You don't think I'm that old, but I am literally that old. And have a cell phone until I was like 22. So again, I recognize that our modern graphing calculators, you can have the option to do log of any base. If you have an old school one, Isaac, do you still have your old school that you had to do the change of base formula on? You're real good at it then. So if you have an older calculator that may not have the log of any base option, most of our newish, in the last 10 years, calculators have that. But I think Isaac must be rocking his dad's from college or something. That's a quality product, though, if it's, going on 15 or 20 years and still holding out. Yes, sir. I think it's the same as the math schedule, I would guess.
I think they're all 80 minutes. No, it's the same. We're just not having community time.
Oh, is that what it is?
Bradley's only 35 minutes.
Oh, beautiful. So they're all 80-minute classes, just like usual. So nothing until community time changed, right? First and second hour still the same start and ends.
Yeah, and I don't.
Yeah, they'll make an announcement. I'm sure there'll be like a bunch of people ask questions. All right. So here's an example of using the change of base formula. So apply the change of base formula to evaluate log base 3 of 16. So you can pick to either use the natural log or the common log. And then you just type that junk into your calculator and out spits the decimal. Or if you are living in the modern era, you can just use the log base option on your calculator. You guys remember where that was at? Should we show you guys real quick? Let's do that real quick. So if you press the math button and you scroll all the way down to the bottom, here it's option A for me. It says log base. And that'll allow you to just type in any base you want for your logarithm. So if I want to do log base 3 of 16, I'm not doing the change base formula with my calculator. I'm just doing log base and just pressing enter. Right? And you should do that. Unless the directions ask you to use log base or use the thingy-majigger. Okay, good. It picked up where I left off. Okay, what about this one? Log base 6 of 10, how do I type that in? Natural log of 10 divided by natural log of 6, right? The argument's on top, the base is in the bottom. You could also use common log. I always pick natural log. Do you know why I always pick natural log versus common log? One less letter to write. Natural log is 2 letters instead of 3. If given my choice, I will always pick the natural log over the common log because it's 1 less letter I have to write down. Yup. And that's mathematician for you right there. So you type that in your calculator, you get the decimal, you round it to 3 decimal places, boom. Or 3 sig figs, I should say. And I think that was the last one. Yup. Alrighty, folks. So, that's it for this. We're going to have some book exercises that we'll add into the problem set for next week. And then, do I have a review for this or not? Are we doing the book review? I have to look at my stuff. Let's look real quick. Methinks it's going to be the book review. But